we now have our designated population of stars. We have a collection of them. We're going to try to understand whether the way we understood the sun with modeling, we can understand how these stars work. We're not quite ready to start with the modeling, because if you tell a stellar modeler, I want you to model a ball of hydrogen, I know its surface temperature and I know its luminosity, he's going to ask you, well, yeah, how much hydrogen is there? We need a way to find the mass of a star. So how do you weigh the star? All we can do is look at it. How do you measure the mass of a star just by looking at it? You recall that we found the mass of Saturn just by looking not at it, but at a moon orbiting it and using Newton's laws. Well, wouldn't it be convenient if we found stars with things orbiting them, not moons, but something we can actually see, so that we could use the same kind of calculation through Newton's law to measure the mass of stars? Well, luckily for us, about a fifth of all the stars in the sky, somewhere around that, are not single stars. They are gravitationally bound to one or more partners. And so, if we can see the partners, we can measure orbital parameters and try to make an estimate of the mass that way. These, if you recall, the picture on the right, is our friend Albireo, the head of Cygnus the Swan, back from Lecture 1. And you remember that we talked about the fact that these are two stars. This is what astronomers, amateur astronomers, like to call a double star. But not all double stars are binaries. A double star is just two stars that are very near each other in the sky. There are two ways this can happen. The two stars could actually be near each other in the world, or they could happen to lie in the same direction from Earth, but at vastly different distances, and be nowhere near each other, as we saw, for example, for the members of the Big Dipper, which are nowhere near each other in the sky. In that case, by the way, we call a false double star, or a double star that is not a binary, is an optical double. A visual binary, like Albireo, is a binary where the two members of the pair can actually be seen and separated. So is Albireo a visual binary or an optical double? The answer is we're not quite sure. How do we tell? Well, we can measure parallax angles for these stars, and they are quite near each other in the sky. Though it's not quite certain that they're bound, for that we measure their motions and try to see whether their total energy is negative or positive. It's not clear whether these stars are bound or not, but they're close to that, so that they're at about the same distance. And with that in mind, let's stop for a minute and appreciate what we've learned just looking at this picture. What can we say that we couldn't say a few weeks ago when we started out and looked at Albireo? Well, we see two stars. We clearly see that one is orange and one is blue. So we realize blackbody spectra tells us that the blue star is hotter than the orange star. We also see that one appears brighter than the other. Since I told you their parallax angles are about the same, that tells you that they're about the same distance. The one that appears brighter is more luminous, so the orange star is more luminous than the blue star. That tells us a third thing. These cannot both be main sequence stars. Along the main sequence, the hotter a star is, the more luminous. Since here we have a cooler orange star, more luminous than a hotter blue star, we have no doubt that one or more of these stars is not a main sequence star. Just looking at the picture, combining it with things we have learned to systematize, we can say some things about this. We'll see later that we have many other techniques. Binary stars are so important that we've developed many techniques for discovering them. Binaries discovered through non-visual techniques where we can't resolve, even in a telescope. The two members are going to be non-visual binaries, and we'll talk about how to find them. But for now, let's talk about a famous visual binary to see what we can learn from it. The star in question is called Alpha Centauri. Alpha Centauri is famous because it's one of the nearest stars to Earth. It's only about a parsec, a little more than a parsec away from Earth. It has, in fact, two members. It's a binary star. The two members are Alpha Centauri A and B, A being the brighter, the primary, B being the secondary. And in fact, we think that the system is a triple star. The third member would be Proxima Centauri, the actual closest star to Earth. Very famous. We're not quite sure if Proxima Centauri is bound to these two or not. If it is, it's a very large, very slow orbit. Let's ignore Proxima Centauri for now. Focus on Alpha Centauri. You see here a plot. We can see both stars. So what we've done here is we've fixed the brighter A component at one point, and then plotted where in the sky the B component would appear. These are right ascension and declination axes, and the scale, or the angles, are marked in arcseconds. Since we know that the stars are both are about 1.3 parsecs from Earth, well, at a distance of a parsec, an angular separation of 1 arcsecond corresponds to an astronomical unit. So the ticks on the scale, the arcsec ticks on the scale, correspond to distances of about 1.3 astronomical units. That means that these stars are orbiting within planetary distances. They're orbiting as close to each other as our planets orbit the sun. This is a very close binary system. And because we know the small angle formula, we can translate angles to distances. That's glorious. In fact, this is not the actual orbit. The actual orbit, the apparent orbit, is this tilted ellipse here. The actual orbit, if you flatten it out so that you see it face on, would be this more broader ellipse here. How do we know that? Well, we can extract the radial velocity of B Alpha Centauri by measuring Doppler shifts, and that tells us how fast it's moving towards us or away from us. Combine that with what we see in the tangent plane, and we get a full description of the motion, just as we did for other proper motions. And this is, in fact, the ellipse seen head-on, and we can measure the eccentricity of this ellipse is about 0.5. It's a rather eccentric motion. The semi-major axis is 23 astronomical units approximately. At their closest approach, these stars are only 11 astronomical units apart, and their period is about 80 years. We can basically, we can plot an ellipse, we measure the speed, we know exactly how fast these stars are going to move, and so we have an 80-year period at a semi-major axis of 23 astronomical units. Now, before we go ahead and take advantage of this, I should tell you that I didn't pick this system just because it's the nearest to Earth. It's also, well, of course, as such, it has been of interest to many science fiction writers, but it's also recently been of interest to scientists because in October 2012, an Earth-sized planet was detected orbiting Alpha Centauri b. Remember we said that it was strange to find stable orbits in binary systems. Even in this very close binary system, there is a stable orbit. Note that the planet orbits very, very near to its star at a distance 10 times closer than Mercury to the Sun. Its period is only 3.5 days or so. This is a very close in, much too hot for liquid water to exist, but the discovery of an Earth-sized planet in a binary system is exciting nonetheless. All the imaginations of what it would be like to live on a planet with 2 suns get fired up and so on. So much for Alpha Centauri. Why do we like binary stars? We like binary stars because when we have a visual binary and we can measure the positions, we can actually predict, just as we did, a projection of the orbit on the tangent plane. Remember, the tangent plane is the plane perpendicular to our line of sight. If we can augment this with radial measurements of the radial velocity from Doppler shift, we can figure out both the motion in the tangent plane. Remember, if this is us, and here is the star, this is the tangent plane, this is the radial direction. Doppler shifts give us a measurement of, in this direction, the astrometry, where we take the distance and the angle and convert it to distance over here with the small angle formula, give us the projection of the orbit on the tangent plane. We can actually produce the orbit of the planets, and in particular we can measure the orbit of the stars, and we can then measure semi-major axes and certainly periods. And if we know semi-major axis and period, we can use Kepler's formula, scale it to the motion, say, of the Earth around the Sun, and find that the total mass of the star divided by the total mass of Earth-Sun system, which to our approximation is the mass of the Sun, is the ratio of the radii cubed divided by the ratio of the periods squared. So we have, since we measure the radius and we measure the period, we can find the total mass of the system. We can do better than that because we plot the motion of both partners in the sky relative to the fixed stars far behind them. We actually find R1 and R2 separately. Remember, the 2 stars orbit each in a circle, or an ellipse in this case, of semi-major axis or radius in our approximation, R1 and R2. And since they're both orbiting their center of mass, these radii satisfy M1 R1 is M2 R2. That's the distance from the center of mass. We know the ratio of the 2 masses because we measured the radii. We know their sum because we measured the period. Between these 2, we can write an easy algebraic equation and find the individual masses of stars. We have a way of weighing stars. This is why we like binaries. Not always are binaries so close that we can distinguish both partners. It's worth figuring out other ways to study binary systems. Let's try that.